Huber laws. Let us learn about Huber laws, which is a regression loss function which tries to take care of both the positives of MSE and MAE. So in the last few lectures, we were learning about regression loss functions. We learned that MSE and MAE, these were the first two regression loss functions that we learned. Then we saw that MSE is having some positives, MAE is also having some positives, this is having some negatives, this is also having some negatives. Then we came up with RMSE, which tried to keep both the positives in it and tried to eliminate both the negatives in it. It was successful to an extent, but what is the problem with RMSE? The problem was that in case of RMSE, always the larger errors were penalized heavily. So this problem you were not able to eliminate. This is not always a problem. In some cases, this may be a problem. Some cases, this may be a positive. Because if you actually want to penalize larger errors heavily, that could be a positive. This time, we are going to come up with Huber laws, which is a different approach to combine the positives of MSE and MAE, and we'll try to take care of this particular problem that RMSE had. Even after we had RMSE, we had a problem that it always penalized larger errors heavily. We are going to take care of that as well in case of Huber laws. So before we begin with Huber laws, I'll jot down few points about MSE and MAE. So these particular points are what we are going to handle. So about MSE, I'll just put down 2 points here. First point about MSE, mean squared error, is that it is smooth and differentiable everywhere. So coming to a regression loss function, we already discussed that it is important that we should be able to take the gradient because this is useful for us in gradient descent algorithms. That is why staying smooth and differentiable everywhere, this is a very positive quality. Second thing is, it penalizes larger errors heavily. This is the second point that we discussed. This could be a positive, this could be a negative. For now, just understand that, okay, MSE is having this particular property. About MAE also, I'll put down 2 points here. First point is, it is robust to outliers. This is kind of opposite of this point. It does not penalize larger errors heavily, because of which it is robust to outliers. This one is sensitive to outliers. Second point is, it is not differentiable everywhere. This is a negative point. So what we are going to do with Huber losses, we are going to handle the negative points. We are going to make sure that won't be there, along with keeping all the positive points there. This is what we are going to do. You can have a doubt here. The doubt can be, how is it possible to handle both these points together? Because these are kind of opposites. You are penalizing larger errors heavily. That means it is sensitive to outliers. If you are penalizing larger errors in a lower manner, not heavily, that means it is robust to outliers. How can your algorithm be both sensitive to outliers and robust to outliers? How is that possible? So this is what we are going to learn in Huber laws. Okay. Huber laws is kind of a hybrid of MSE and MAE. What we'll do is, first we'll write the loss term, or you can call it as the residual. So you can call R is equal to Y minus Y cap. What is this? You are having some input X, Y. See, I'm repeating this part in every lecture because this is very important and I want this to be stamped in your mind. If you have an input X, Y, in which X is the input and Y is the expected output, then if you have a model M here and you input X into this model, what happens? Model provides an output Y cap, which is the prediction by the model. You now have to compare this Y cap, which is the prediction by model, with actual Y, that is the actual expected output. How much is Y cap deviating from Y? This is the error. So your residual is Y minus Y cap. How much are these two values differing? This is your residual. So all the error functions or loss functions, these are all different attempts to mathematically represent this particular value such that it is useful for modeling a machine learning model. This is the whole concept. You have the residual here. Let us see how to find out Huber loss. Huber loss L delta of R of the residual. So I'm writing in terms of residual so as to make it simpler. Residual is this particular term. I don't want to repeat y minus y cap everywhere. It has two formulas depending on the situation. This is how it is taking care of both MSE and MAE. Okay, let us see how two formulas work here. First formula is half R square, which is actually the MSE formula, mean squared error formula, half of residual square. The other formula is delta into mod R minus half delta. So this formula is somewhat similar to mean absolute error. So you have two formulas here. One is MSE formula, one is MAE formula. The next question is, when are you going to use this formula and when are you going to use this formula? The answer is, there is something called as delta. This delta is a threshold that you have to define. It will always be greater than 0. This delta, you can call it as the tuning parameter or you can call it as the threshold. So this particular threshold, how it helps us, in case, let me erase this part off. Okay, this should be used if your residual mod R, so I'm writing mod R because y minus y cap or y cap minus y, whichever is larger. So if this is less than or equal to delta, if mod R is less than or equal to delta, then you will be using the formula which is related to MSE, the mean squared error related formula. Otherwise, this will be used if mod R is greater than delta. That means whenever your residual is larger, whenever your error is larger, you are going to use mean absolute error formula, which would mean larger errors are not penalized heavily anymore. Whenever your error is smaller, you are going to use MSE formula, mean squared error formula. That means it encourages quick convergence like MSE. What is the speciality of MSE? Because the gradient will also increase linearly with errors, it encourages quick convergence. So whenever you are designing a model, if you are using MSE, in each step, it will take a larger step in modifying the parameters, which will help you in reaching a convergence in a quicker manner. This is the advantage of MSE. So whenever error is smaller, you are going to use this formula and go the MSE way. Whenever error is larger, it is greater than delta, then you are going to use MAE formula, which means larger errors will not be penalized heavily. So this would mean outliers won't blow up the loss. This is the whole point. It is robust against outliers. So what did you understand now? Now you understood that Huber loss, this is quadratic near 0. If you look near 0, there it is quadratic. But if you go far away from 0, then it is linear. This is the point. Next step that we have to do is gradient. So what I'll do is, I'll just write gradient values here. So this is the loss. If I take gradient del L delta of R divided by del y cap, this is equal to, there will be two gradients. First one is, so I'm directly writing here y minus y cap, similar to the gradient of MAE, if mod R is less than or equal to delta, and it will be minus of delta into sine of y minus y cap, sine of y minus y cap, if mod R is greater than delta. So there are two possible derivatives depending on what exactly is the residual, whether it is less than or equal to R, or if it is, less than or equal to delta or greater than delta. So I directly wrote the formulas here because you already know about MSE and MAE. Or let us solve this. That's better. There should be no confusion left. We'll just solve this out. Okay. Let us see how exactly this derivative came. See, I'm solving this because as a machine learning student, you should know how to calculate derivatives. This is an important part. So if you know this, then whenever you are handling gradient descent or something, it's easy for you because you know that whenever you got any particular loss function, you can easily find the derivative. You see what is the slope, what is the adjustment to be done in gradient descent algorithm. So we'll just see how these particular gradients came. This is an important part. That's why I'm doing again. I initially thought I'll simply write. It's better I solve this. Okay. We'll take the loss and we'll solve this. So what did we discuss about loss? L delta of R. This is equal to, we discussed that it is half R square when mod R is less than or equal to delta, and it is delta into mod R minus half delta when mod R is greater than delta. We are going to take both these cases and we are going to find the derivative. Okay. So first of all, let us take this case, the first formula. In that case, we are going to find derivative with respect to R first. Actually, we want to find del L delta by del Y cap. This is the requirement. So first what I'll do is, first I'll take derivative with respect to R. Then we'll use chain rule and we'll find the final derivative. Okay. So the derivative with respect to R, in case mod R is less than or equal to delta, in this case, dl delta by dr, this will be, so this is the formula I'm using, this will be d by dr of half r square. What will this be? Square will come to the other side. Here it will come, 2 by 2 will be 1. So the remaining will be r. So dl delta by dr, this will be r. So if you take the gradient with the MSE formula, that is in case mod r is less than or equal to delta, then d delta by dr will be equal to r. This is the first part. Second thing we are going to solve is, what if mod r is greater than delta? In this case, if you take dl delta by dr, what happens? This will be d by dr of, what is the formula? Delta into mod r minus half delta. This is the formula. If you take the derivative, see, this term is not having r at all, which means this is going to go to 0 when you take the derivative. So this part you can ignore in the next step, because half delta, if you take derivative with respect to r, it will be 0, right? So this is equal to, so only this term is relevant now. So delta we'll take outside. Then you need d by dr of mod r. What is d by dr of mod r? This will be sine r, right? Sine means sine of r. When I say sine, here also I put sine. I didn't explain what is sine. So when I say sine, the sine formula, if I write sine of x, what does this mean? This means whatever is the sine of x, if x is greater than 0, answer is plus 1. If x is equal to 0, answer is 0. If and x is less than 0, answer is minus 1. This is what I meant when I wrote sine of x. Okay, whatever is the sine of x, if sine is positive, then derivative it is plus 1. If sine is less than 0, it is negative, then it is minus 1. It is not the actual value of x, but just minus 1. Okay, when it is 0, it is 0. This is what I mean when I write sine. So here when I write, this is equal to delta into sine of r. This means whenever the value of r is greater than 0, this will be plus 1. This part will be plus 1. So it will be my plus delta. Whenever the sine of r will be minus 1, that is, if r is less than 0, then answer will be minus 1. For sine r, it will be minus delta for this particular term, right? So this is the dl delta by dr component. Now we are going to apply chain rule and we'll try to solve this. Okay. How are we going to apply chain rule? For applying chain rule, first thing, what are we going to find? Del L delta divided by del y cap. This is what we actually want to find. So your loss is this term. You want to find derivative with respect to one particular prediction y cap, right? That is the requirement. So what we do here is, We'll take this. We are going to apply chain rule. I already told you we want to apply chain rule. How do you apply chain rule? dl delta by dr into dr by dy cap. This is how you can apply chain rule. This dl delta by dr term is already there with you. So the other term which you don't know, this term you already know because we computed here. For both cases we computed. The term which you don't know is this term. It is dr by dy cap. So let us first conclude on this. Let us first take this term. We'll clear this out. Once you understand this term, remaining is easy because you already know what is this term. If you do this, what is your r? Your r is y minus y cap. This is your r. If you take dr by dy cap, what happens? Y, if you take d by dy cap, it will be 0. Y cap minus y cap, if you take dr by dy cap, it will be minus 1. So the value of dr by dy cap is minus 1. What did you understand now? Instead of this, you can substitute minus 1. That means this term will become minus of dl delta by dr. So whatever you got here, the negative of that is your actual derivative. So what is your del L by del y cap? This can be written as negative of whatever you got here. So whenever mod r is less than or equal to delta, your del L delta by del y cap, this will be negative of this term. So that will be minus r. So whenever mod r is greater than delta, then your del L delta by del y cap, this will be negative of this term, that is minus delta into sine of r, right? So these are the two derivatives. Now let us go back and look at what I initially wrote. See this term. This is exactly this. What is your r? R is y minus y cap. This is your r. What did I write here? Minus r. Here it is minus of y minus y cap. What did I write here? Minus delta into sine of r. R is y minus y cap. Here whatever I wrote was minus delta into sine of y minus y cap. So I just gave you complete derivation of how exactly I reached here. Okay, so now you know this is the derivative. I'm going to remove, okay, let it stay there. So as of now, just understand that this is the loss function. Then this is the derivative that you got. From this derivative, what did you find out? This derivative is very similar or exactly that of the MSE derivative, which means error increases linearly. Error increases linearly with the magnitude. That is, whenever your error increases, your gradient increases linearly with your error. That is whatever property MSE had. The same thing is here in case of Huber loss. Keep in mind, error increases quadratically because of MSE formula, but your gradient is found by taking derivative when differentiated the error, which means the quadratic term when you differentiated became linear term. That is why your gradient will increase linearly with the magnitude of error in case of MSE. That is this particular case. What about this case? Here it is not linear. It is not dependent on the magnitude. You are only considering the sign of error. You are not considering magnitude. That means whenever mod r is greater than delta, whenever the error is larger, you are not going to consider the magnitude. You are only going to consider the sign of the error. That means it is always plus or minus delta that is going to be the gradient, right? So this is where it is not going to penalize larger errors heavily. So one more thing before we conclude, we'll just see where do you use Huber loss. Okay, we already discussed about multiple loss functions. So somewhere you should be clear about where to use Huber loss. One is robust regression. Why is it robust? Whenever you don't want to penalize larger errors heavily, that is robust. Okay. So when data contains good amount of outliers and you want it to be there, so you use Huber loss. Next thing is whenever you want to balance out speed and robustness. This is the most important part. Speed and robustness has to be balanced out. Because of this MSE term, it will converge fastly. So it will have speed. Because of this MAE term, it will have robustness. So whenever you want speed along with robustness, if you use MAE, it won't have speed. But here, it has both speed and robustness. This is where you make sure you use Huber laws as your regression loss functions, right?